Okay. We start with the session. Good afternoon. We are happy to present this new seminar within the series under the title Test and Invited Paper Seminar Webinars, promoted by TEST, an official journal of the Spanish Society of Statistics and Operations Research, acronym SEIO, published by Springer since 1992. It was formerly Trabajos de Estadística since 1950. So it is about 75 years of history now. So first, we thank again SEIO for providing full support to the organization and diffusion of this webinar. As you well know, the journal TEST has a solid internationally recognized reputation for diffusion of high-quality level research in statistics and probability, covering in a broad sense theoretical and methodological contributions in this area with applications in perspective. The editors-in-chief of TEST starting 2025 are Professors Gonzalo García Donato and María del Carmen Pardo. And you can see the renewed composition of the editorial board in the journal website. The journal TEST is indexed in particular by Clarivate Analytics, Web of Science, with an impact factor rank position currently, still from the 2023 reference information, slightly above the median in quartile Q2 in the category statistics and probability. In some of the 4 issues published within each year volume, TEST includes an invited paper with discussions by outstanding researchers in selected frontier topics. As is the aim of this series, the authors and discussants are invited to give a webinar on their recently published contribution, which we firmly believe offers an exceptional opportunity for extra diffusion, direct interaction, and further potential exchange with the interested audience. Just to let you know that these webinar sessions are recorded, of course, with the permission of the participants involved, and will remain available in the SEIO YouTube channel. Today, we have again an exceptional speaker on a new interesting paradigmatic topic. And now I leave my colleague and former co-editor-in-chief, Ana María Aguilera, with the presentation and moderation of this session. So thank you and welcome.
It is also a great pleasure for me to be here today organizing this seminar. We are very honored to welcome Dr. Prothero as the speaker for today's webinar on data integration via analysis of subspaces, DIVAS. Before introducing the speaker, I would like thanking him and his co-authors, Professor Jiang from Meta, USA, Hannig, Tran-Dinh, Ackerman, and Marron from the Department of Statistics and Operation Research, University of North Carolina at Chapel Hill, USA. Thank you for writing this really interesting and innovative invited article published in the last September issue of TEST. Dr. Prothero is a distinguished mathematical statistician in the Statistical Engineering Division of the National Institute of Standards and Technology Laboratory, where he specialized in statistical modeling, uncertainty quantification, and high-dimensional data integration. He received his BS in mathematics from the College of William and Mary in 2016 and continued on to the University of North Carolina, Chapel Hill for a PhD in statistics and operation research. After defending and graduating in 2021, he joined the Statistical Engineering Division at NIST in August of that year. Dr. Prothero has contributed significantly to forensic science and environmental research, developing statistical methods for forensic drug analysis and uncertainty quantification in emissions inventories. His research interests include data integration, object-oriented data analysis, and spatial data analysis. Beyond research, he is an experienced teacher in data models, inference, and decision modeling at University of North Carolina, Chapel Hill. He has also led hands-on workshops on measurement, undertaking, assessment, and national training symposium. We are excited to hear from Dr. Prothero today as he shares insights into data integration via analysis of subspaces and its applications. I apologize for not being very shouty, but time is limited, and both the invited speaker and the discussant in this seminar are excellent researchers with extraordinary curricula. So, Jack, you can begin. The word is yours.
Okay, thank you so much, Anna, for the wonderful introduction. Good morning, everyone. I guess it's afternoon for you, it's morning for me. Sorry, I'm a little under the weather this morning. So sorry for that with my voice, but let's get started. So I'm going to talk about what motivated us to put this method together, to research in this area in the first place, what exactly constitutes this new method we've developed, and then we're going to take a look at a quick case study example to finish off. So we were encountering more and more situations where the data we were interested in analyzing spanned very different kinds of data collection paradigms. I've got on the screen right here a couple different looks at neurological data. On the top, I've got one view of sort of functional connectivity in the brain and structural connectivity in the brain. And on the bottom, I've got a different view of that. And those two things are something that naturally we would want to study together. And so we're looking for ways to analyze those simultaneously to see how they might be related to each other, how they might differ, and in addition, start to incorporate some other information we might have about people in these studies, because it's not just brain imaging. We have, maybe they've taken some surveys about their behavior. We have demographic information. And that's also something we want to integrate into these kinds of analyses to make sure that we're capturing all the potential relationships. Another natural area where this type of data comes up is cancer genomics, where we've got on the right side of that figure there several different sort of omics platforms: gene expression, gene copy number, protein expression, mutation events. All those sorts of things are known to impact the incidence of cancer and the types of cancer that arise over time. And so this makes for another natural situation where we want to figure out where the similarities between these different measurement paradigms are, where are the differences, what are they telling us as a unit. And so the questions we're wanting to answer is, how do we leverage that shared information to the fullest across all the different data blocks? And as these situations become even more complicated, how do we account for large numbers of data blocks? Because I know earlier situations, we might think about, oh, we have 2 things that we want to analyze together, 3 things we want to analyze together. What do these situations start to look like as that number starts to grow, 4, 5, higher? And so I want to take us through a little bit of maybe a walk down memory lane, a walk down the history of different attempts at answering these kinds of questions. And so I'll have a couple different pictorial representations of different integration methods. The first being sort of a principal components analysis, where we ignore the fact that all of our features of all of our data are coming from different sources, different measurement platforms, and just saying, hey, let's look for where the highly variable directions seem to be if we just throw all the features we have into one big pot, stir it around, and see what happens. And so this works okay, probably in some situations, but we lose all of that structure that we know exists in the data coming in. So next step here, we might consider something like canonical correlations analysis or partial least squares, where we now consider the structure in the data, and we then look for sort of directions in the subspaces spanned by each of these data blocks that are highly correlated, highly related to one another. And so we have this sort of connection between the data blocks. There's some information there, but we thought the steps of this path of research continued beyond just looking for related structure between data blocks. We then get to the joint individual variation explained, jive, ajive family of methods, where the assertion changes a little bit, where instead of just finding related structure between data blocks, we're now looking for an assumption that there is some specific underlying structure that is actually shared perfectly between all of the data blocks. We've made a leap in the assumptions in the model of what we think is true about the data in truth. And so instead of just finding related structure, we're finding a single direction or a set of directions that we are asserting is truly shared, truly latently underlying among all of the data blocks, and then separating that out from structure that we think is still important in the data, but is not shared between all of the data blocks. And so then the last step here, at least the next step here, is thinking about, well, I've left some space in the middle there, and you might imagine that there are some situations where if we've got 3 data blocks, not only is there stuff that's shared between all 3, but there might be stuff that's shared between just the first 2 or just the last 2. And so we feel that this sort of breakdown is potentially more informative, more appropriate in some data integration cases where we think that there are relationships and sub-relationships between all of the different data blocks, all of the different measurement paradigms that we're trying to consider in an analysis. And so this is going to be our proposed model for DIVAS, data integration via analysis of subspaces, of trying to capture that shared structure at all steps of the hierarchy. And so I've got, just as a guiding light thing, we're going to revisit this a little bit later in the talk. I've constructed sort of a toy example that might be the ideal case for something like this, where on the left, I've got sort of the data shown in a heat map view. We would observe only the stuff on the left side of the equal sign. And on the right, we show how that data was constructed. That second column, we've got sort of 3-way shared structure, that pinstripe. So that's that shared information between all 3. And then we can also see that there's pairwise shared information across each pair of blocks as well that gives us the ultimate data. We see no individual structure here, just to keep it simple. One little note I'll just throw out there while we're looking at this. Astute viewers might notice that sort of the shared structure, the row structure of the pairwise block collections are not fully orthogonal to one another. I think the angle is about 60 degrees between that one-dimensional subspace between the first 2 blocks, the one-dimensional subspace between the first and the third block. And just keep that in mind. We will be able to pick that apart, even though they're not perfectly orthogonal in truth. But yeah, just this is the kind of thing to keep in mind of the data is not always going to look exactly like this, but assuming the data looks something like this is what we're going for. How exactly are we going about this, where we just have that data on the left and we want to end up with kind of an estimate of all of those matrices on the right in that figure? How do we go about that? So here's our assumed model for each data block. We've observed the data and we assume that the data is an additive combination of a fixed rank signal matrix and a noise matrix with some sort of typical variance assumptions, moment assumptions. And then we've also got this maybe a little bit atypical assumption about the noise here in this last bullet point, what we're calling rotational invariance between the signal and the noise. I will get into a little bit more detail about what exactly we mean by that in a couple slides. One noise structure that does satisfy this rotational invariance is if we assume the noise is Gaussian. It's a little bit more general than that, it turns out, but just as getting it in your head of what this assumption means. Gaussian is one way to satisfy it, Gaussian noise. And so now we're going to further think about those signal matrices and what exactly are we assuming about the structure of the signal matrices. We are assuming that they are a sum of a combination of scores and loadings, and each scores loadings combination is associated with a block collection. So we might have one term of this sum for blocks 1, 2, 3, one term of this sum for blocks 1, 2, one term of this sum for blocks 1, 3, one term of this sum for blocks 2, 3, and then some individual ones as well if there's structure like that. So each component of the sum is a scores matrix, which is that identical shared structure we assume between all the blocks in a block collection. And then corresponding loadings matrices, which naturally have to be specific for each data block because they might have different numbers of features, but they are entwined with the fully shared scores matrices. And then I got to emphasize this bullet point here a lot because I think exact basis vectors we end up with for these spaces, we're concerned about the subspaces themselves. That's why we have subspaces in the name, data integration via analysis of subspaces, because our fundamental unit of structure here is the subspace, not necessarily the vector or the matrix. It's about what subspace that matrix is defining. And we have some identifiability conditions here to make sure that this all works out well. I won't go into them in too much detail here. There's a more full discussion of this in the paper, but just know that there's some underlying additional things here with the signal matrices. And so we're going to go through this in 3 steps. We first need to estimate the key information about each data block separately. How much signal do we think is there? And something called angle perturbation bounds for each data block. Then we will throw all that information together and figure out where is that joint structure shared between collections of blocks, and then put everything back together so we could have a version of that nice picture we had of the toy example a couple slides ago that's estimated for everything. So first step, I would say this is the step that I think had the most thought put into it as far as new stuff. So our goal here, if we've got a data block, is we're sort of trying to estimate from that data block, what are the subspaces in row and column space, in trait space and object space of the signal associated with that data block. Natural problem here, when we're assuming that the data is signal plus noise, when we add that noise to that signal, those subspaces are perturbed both in magnitude and in orientation. Now the magnitude, that's pretty recoverable. There's a lot of work out there on this of sort of matrix signal extraction, matrix signal recovery. We just do some singular value decomposition, do some shrinkage on the singular values we get. This work is from Gavish and Donahoe a couple of years ago. And so we get a good estimate of the magnitude of the signal from this process, but the orientation is a whole different story. The exact orientation, actually, with the assumptions we have in our model, the exact orientation isn't really thought of as recoverable. So what do we do instead? Because there's no way to know sort of exactly how we should rotate the answer we got in magnitude to get the best answer. And so our approach is to instead construct sort of a confidence region around the subspace that we identify as potentially containing the signal. Sort of like getting like a cone around the subspace. And that cone contains what we see as feasible orientations of what the true signal might have been given what we see. To get more specific, it's just a collection of vectors such that the angle between that vector and our estimated signal subspace is below a certain angle bound. And this kind of math also works both directions. We emphasize the math in Rn just because that's where stuff is fully shared between blocks, but there are, of course, corresponding vectors and associated angle bounds and associated subspaces in the other space in RdK for each block K. And so the sort of the $1 million question is, how do we get these angle bounds? How do we pick them in a principled way so that this confidence region behaves the way we want to? And this could be a whole talk in and of itself. Long story short, we use a rotational bootstrap, so to speak, that this is where that assumption comes in of the relationship between the signal and the noise, that rotationally invariant relationship. What that assumption gets us is that we can produce bootstrap replications that re-rotate the data and preserve the angular relationships between signal and data. And so even though we don't actually know what that relationship is, we can, in truth, we can sort of replicate it and get, okay, what do we think the angle between the signal and the data might be, and get a guess at what these angle bounds need to be. And so now, after that step, we have our 2 angle bounds, one for trait space, one for object space, and we also have the estimated signal rank for each data block. We can now estimate where we think the joint subspaces are for each block collection. We start from the largest block collection with all the blocks and then move sequentially down to the individual blocks one at a time. And we work with an optimization problem that I'm going to show now here. Our objective is to minimize the angle of a given direction, the sum of the angle of a given direction between each of the subspaces we're considering in the current block collection. And then we just have a couple constraints on what those angles are. They naturally, for each block that's included, the angle between our considered direction and that subspace needs to be less than the angle bound we calculated. We then also assert that any direction we pick needs to be far enough in an angular sense away from a block that's not included. So if we're looking at the structure between blocks 1 and 2, we're trying to pick a direction, that direction needs to be far enough away from block 3. That's what that last sort of angle constraint is. Because if it was close enough to angle 3, then it would be three-way joint, not two-way joint. And then naturally, just to make sure we're finding kind of a full subspace with each of these things, all directions we find need to be orthogonal to all the previous directions we found for this block collection subspace, and also needs to be orthogonal to any subspace we found for a block collection that fully contains the block collection we're currently considering. So if we found three-way joint structure, all of the pairwise joint structure is going to be orthogonal to that three-way joint structure. But if we're looking at the difference between block collection with 1 and 2 and 1 and 3 together, those don't mutually contain each other, so those won't have to be orthogonal. But if we then move to individual, say block 1, individual block 1 is going to have to be orthogonal to the stuff for block 1, 2, 3, the stuff for block 1, 2, and the stuff for block 1, 3. So that's what that last constraint is with that sort of block collection subset thing on the bottom right. And so we implement this with sort of a convex concave penalized algorithm from these nice folks to get our answer. And once we have all of those subspaces, those basis vectors for subspaces for shared structure between all of the block collections, we can then back that out into the corresponding loadings matrices that work for each individual block associated with each block collection's shared subspace. And now because we're not fully attached to the basis vectors, we care about the subspace, we can perform some quick sort of re-rotations that we think help for interpretability of the subspace, but any orientation of the subspace is okay with us. And like I said, we just sort of back solve given the scores that we found for each associated shared subspace to get the loading matrices for every block. And then just to have a quick example of what that might look like for one of the things from our toy example earlier. On the left, we have the estimated component of the signal matrix for block 1 associated with the three-way shared information. And on the right, we have the true component of that signal matrix that was used to create the data. As you can see, we do a pretty good job. There's a little bit of fuzziness on the left. Of course, it's not perfect, but this is the results of our estimation on that toy example that was specifically made to work well on this method. So now let's wrap up the last couple minutes here with a case study. And our case study here is mortality statistics over the last couple of centuries. And what I mean by mortality rate, mortality statistics, what that means is for every age for a given year in a given country, you look at how many people passed that were that age that year as a proportion of the total number of people in that country or area that were that age that year. And so those are the statistics we're working with. On the left, we have what that looks like for Spanish women over the range, the time range of our data set. Each line is a year, and the horizontal axis is age, and the vertical axis is that mortality rate. We've taken the logit of it, we've transformed it. But so those are our sort of data objects that we're working with. We span 1908 to 2018, and we have, excuse me, 4 total data blocks of both men and women from both Spain and Switzerland. And we use ages 12 to 90. And so we think about our analysis thought of this as sort of the ages were the traits or the features, and that the years were the observations. I think we potentially might be hearing from Eirik later today that because all of these data blocks are the same in numbers of features and numbers of traits, you can think about it either way. But that's how we will think about it here. And so what we'll be looking for is we'll be putting these 4 data blocks into DIVAS and seeing what shared subspaces we find. And so we find a 2-dimensional 4-way shared subspace between all 4 data blocks. And when we're looking at these plots, what is often helpful to look at is what years, because the years are the colored lines, what years are most different from each other? What years are being contrasted by this subspace? And so if you look across this first row, there's a big contrast, there's a big comparison between the purple years and the red years, the oldest years and the newest years. And what we interpret this as is that there's been overall improvement in mortality rates over the 20th and 21st century. No story there. In particular, this sort of contrast between sort of the young side and the old side, because remember the horizontal axis here is age, is we interpret this as a greater improvement in mortality rate for younger individuals. And so in addition to that sort of obvious trend you saw on the previous slide of years go on, mortality rate goes down, this is a specific improvement in mortality rate in a subset of the population by age. And then the second component here of this subspace that's orthogonal to that first one, we might think of as, okay, there's sort of a contrast between early middle and late middle age, and then the years involved are not just the early and the late. It's like the green and red, and the green is sort of the early 70s, late 60s, and the yellow and red is sort of the turn of the millennium. I know this is often interpreted, one possible thing that this could mean is sort of, it's colloquially referred to as sort of the seatbelt effect, where seatbelts were not mandated in cars, and once laws went into effect that mandated them, there was a noticeable drop in mortality for young, reckless people that were speeding and not wearing seatbelts. We additionally find a one-dimensional 3-way shared space, excluding Swiss women. It has Swiss men, and Spanish women. And then again, the contrast is sort of young versus middle age, but the years are a little different. Now, on one side, we have sort of a yellow range that's starting to get into the 80s and 90s, and on the red, we have solidly into the new millennium. Our hypothesis here is that this is detecting excess mortality associated with HIV/AIDS. Just a hypothesis, but just thinking about the age groups, the year groups, and things that might be associated with unique mortality events. So that was what we were able to find shared across these data blocks. So looking forward, I really appreciated all the discussion we got from other folks that gave our paper a good read and a good think. I think there were 2 common themes that were drawn out from what I was reading from everybody. One was that there's a desire for this kind of analysis to be performed on more complicated data, more sophisticated data, more bespoke data, things like text information or data where we wouldn't expect the relationships to all just be linear, right? Because we're just dealing with subspaces. Everything's been linear so far today. And so thinking about what modifications to the method are possible to handle those situations. And also, I think a wonderful point that was brought up by many that I think is something that this field needs to answer pretty quickly is, what does uncertainty quantification look like for the outputs of these kinds of models? And that goes 2 levels, right? We have on one hand, did we get the subspace right? Are we off in angle? Are we off in magnitude? And the other hand is, did we assign structure to the right place? Did we assign it to 4-way when it was actually supposed to be 3-way? And how do we disentangle those 2 sort of modes of uncertainty? How do we know which is one, which is the other? Lots of questions there. And I think some of our discussions will be talking about that too. But those were just some common themes I noticed that I was excited to hear more about and think more about. And I think I will leave that there. That's my contact information. Thank you so much for the opportunity to present this.
Thank you, Jack, for this nice presentation. Now we are going to begin with the discussion. We are honored to welcome Dr. Irina Gaynanova as a discussant in today's webinar. Professor Gaynanova is a leading expert in statistical learning, data integration, and high-dimensional biomedical data analysis, with a special focus on multi-omics and wearable device data. She is currently an associate professor of biostatistics at the School of Public Health in the University of Michigan, where she develops cutting-edge statistical and machine learning methods for complex biomedical survey data. She holds a PhD in statistics from Cornell University and has held faculty positions at Texas University. Professor Gaynanova's outstanding contributions to statistical research have been recognized with numerous awards, including the NSF Career Award and the INS Myrvoll-Nilsen Emerging Women Leaders in Data Science Award. She is also an elected member of the International Statistical Institute. She's a very expert researcher in statistics with notable results published as articles in highly reputable journals. He's also known for his leadership in managing funding projects as well as his multidisciplinary collaborations with other areas and prominent collaborators in statistics. Beyond her research, she is an associate editor for top journals, including Biometrica and the Annals of Applied Statistics. She has developed several widely used R packages for statistical data analysis and is actively involved in mentoring the next generation of data scientists. We are thrilled to have Dr. Gaynanova with us today to share her expertise. Please, thank you. You can begin.
Thank you for such a kind introduction. It's very humbling, and it's such a pleasure to be here. And before I start, I just wanted to acknowledge that a lot of the comments, a joint work with a former PhD student from Texas A&M, Rinat Sergazinov. And I'm going to talk about just a subset of the comments that were made. And so to remind, as we just heard this presentation about DIVAS, which is a new method for identification of different structure types from noisy multiview data. And from our perspective, there's a lot of really interesting highlights, in particular this idea that if we can find basis directions that are simultaneously within the perturbation bound, then those basis directions should correspond to the shared structure. I really like the rotational bootstrap idea for the perturbation bound estimation and residuous noise correction. I think idea of aligning simultaneously the object space and the trace space has not been explored in the literature so much. And of course, I think the key contribution of the work is the principled way of how do I identify partially shared signals and how do we define them. And so in my discussion here today, I would like to provide a brief comparison and connection with existing decompositions focusing specifically on partially shared structures. So I know that Jack didn't go into identifiability conditions as much. This is going to be more the focus of my discussion, and I'm going to simplify it a little bit for us, looking at the free view decomposition case. So this is the true signals, A1, A2, and free. And in this case, we can think of getting them into flow blocks like Jack demonstrated. And just for ease of following, I'm using the red to define the fully shared structures and blue to define individual structures. And sort of for the first mode of comparison, I'm going to compare with slide, which is our previous approach. And from sort of similarity perspective, each of the blocks here is decomposed in scores and loadings. And the V's are the ones that are shared within each of the block. And the key difference that Jack alluded to is that in slide, the full orthogonality is assumed across all of the loadings. So this matrix phi becomes a fully orthonormal matrix. That was convenient from the estimation perspective, but it actually led to some identifiability issues. And as Jack alluded in DIVAS, orthogonality only across the structure type within each view is required. That is, the red is orthogonal to black, is orthogonal to blue, but there is no assumption of orthogonality within the black part or within the blue part, and that really makes the model unique and identifiable. The other method that I would like to compare it is with HNN, which stands for hierarchical nuclear norm penalization. It's a more recent approach, and it's also getting at this idea that Jack mentioned, that we're really interested in the subspaces rather than individual basis vectors. So the way the DIVAS is presented and developed, it's presented in terms of the decomposition of the signal matrix itself into these 4 blocks, and then there is a scores and loadings factorization for each of the blocks. The way HNN approached it is directly looking at the decomposition on the row spaces or the trait spaces as they are named in DIVAS, and basically looking at the decomposition of the trait space as a sum of the free subspaces. And I'm using the same color to emphasize that even though the notation is very, very different, the iteration is very much the same, and in particular, the key part is this same partial orthogonality assumption. That is orthogonality across structure types within each U, so that red is orthogonal to black, is orthogonal to blue, but no orthogonality within individual across the blue ones or within the black ones. And those 2 models, as we demonstrate more carefully in the comments, are actually exactly equivalent, which was a very, very nice thing to see. And I'm just going to provide you some intuition for why this is the case. So first, I'm going to do sort of a little number illustration. Those are very free toy matrices. So Jack already illustrated them with colors. I'm illustrating with numbers just to give the same ideas. So in this case, you can think that the top red vector is basically the shared or joint structure across all 3 of the views. It's a contrast between 1, 3, 5, and 2 and 4. The orange here is a structure that is shared between A1 and A2. The bolded black is A1 and A3, and then everything that is left is individual, and within the first matrix, there's nothing individual left. And looking at the numbers directly, hopefully it's more clear that if I look at the orange for A1 versus the black, these 2 basis vector, the basis vectors that form those 2 linearly independent, clearly, but they are not orthogonal. There is some inner product here. Similarly, for individual, if you compare the 2, they are linearly independent, but they are not orthogonal. And it turns out that this is a more difficult condition to write down, as I'm sure Jack knows as well, but that is really what is required for identifiability. And kind of to illustrate again why doing this assumption on the trait spaces or the raw spaces is the same as doing this assumption on the loadings and the scores. Once you have sort of decomposition on the row spaces, then you can write the projection matrix onto that row space as the sum of the projections due to the orthogonality. So that means that when we look at the signal matrix, we can represent the signal through the signal and the projection on the row space. And sort of going through relatively simple algebra here, we right away get 3 parts. So we get the joint part, we get the partially shared part, and we get the individual part. And then the partially shared part separates into the 2 exactly due to those linear independence conditions that are put in the loadings. So all of those conditions come together and the decompositions coincide. So the fact that we arrive from same models from different approaches, I think, is really exciting. I feel like this is a fundamental starting point for future developments and partial shared structure learning. The estimation approach between the 2 methods couldn't be more distinct. DIVAS, we saw that sequential estimation for basis vectors looking at the perturbation bounds constraint. HNN is a little bit more ad hoc, but there's a joint penalization looking at the hierarchical nuclear norm constraints. And looking at how sort of the same model can use 2 very, very different estimation approaches, I'm very excited about future possibilities now that we know what the right model is. Can we try to combine their ideas and perform joint estimation of all the subspaces within this framework? And I think that's a very exciting direction to pursue. And to conclude, we congratulate the authors on this exciting work. And I want to sort of end this discussion with a question: how do we measure the structure estimation accuracy? Because if we look at the sort of continuous estimation accuracy, where we just look at each of those signals and we compare the true signal matrix with the estimated signal matrix, this error does not reflect errors associated with subspaces, not directly at least. At the same time, if we try to look at the structure-specific measures, even if we sort of limit ourselves to the very simple 2U case, this can be very misleading under slight perturbations. And I'm going to conclude with this final toy example for us to maybe ponder a little bit on, where we're back into the very simple 2U case. We have a joint structure in red, we have an individual in blue, there is no partial share in here. And let's say our true joint structure is just rank 1, so we only have the red part, and we have our shared V12. And then we happen to misidentify the rank. We happen to not realize that we have the joint structure, and instead we estimated rank 1 individual for each view. So in our estimated signals, we now have the blue. We have different V1 hat and V2 hat, but we weren't that far off. Each of them is pretty close in inner product to the true joint. So looking at this example, that you see that if we look at the matrices at the red and blue individually, we will have huge errors on all of those structures individually. But if we look at the vectors and then look at the inner product, we are sort of on the right direction. So how do we think about evaluating these errors and quantifying these errors so that we respect the structure but also not way off, is I think something that I'm still pondering on. I think we will be pondering on, and I think it's really exciting to pursue and very important. With that, I will conclude. Thank you very much.
Okay. Thank you, Irina, for these really interesting comments and very expert comments on this paper. Now, Jack, do you want to give a response to Irina, or even Professor Marron, who is also here as co-author? You have the
yeah, I mean, I couldn't agree more. I think, when I read your comments, I was like, holy cow, we ended up with the same thing. That just blew my mind. And yeah, I agree similarly. Whenever I go to okay, how do we differentiate these different kinds of errors we can make? I think about it, and then I kind of like, what does this even look like? I know the person I cited at the very beginning with those neuroscience and neurological measurements, Andrew Ackerman, who actually just defended a couple weeks ago, he did some preliminary work on some stronger diagnostics on subspaces. So not talking about sort of rank of misidentification or misallocation of structure, but I think there's some exciting work happening there, at least with getting a better diagnostic of have we gotten the orientation right. And
very nice.
There's starting to be some progress on that.
Yeah, Irina, thanks very much. I appreciate the comments. I really like this idea of coming to the same point from 2. That was a brilliant observation. And I also really like your point about we need to figure out what happens when we misidentify the rank. If indeed that can happen, I think we've got to figure out a way to study that explicitly. Great comment. Thanks.
Thank you. It's been a very enjoyable paper to read, so it was very easy to write the comments.
Okay, thank you, Irina. Have you a nice...
Thank you, and I apologize again that I have to leave earlier.
Okay. Now, the second discussion is Professor Hai Xu. He is assistant professor in the Department of Biostatistics at New York University. He received a PhD in biostatistics from the University of Michigan and a BS in Information and Computational Science from Harbin Institute of Technology, China. Before joining New York University, he was a postdoctoral fellow in the Department of Biostatistics at the University of Texas, MD Anderson Cancer Center. Dr. Xu serves as an associate editor for Statistica Sinica and the American Statistician, and is an editorial board member for BNC Artificial Intelligence. His research focuses on high-dimensional data analysis, particularly data integration, as well as machine learning, deep learning, medical image analysis, and genomic data analysis, with applications in Alzheimer's disease, brain tumors, and breast cancer. As a result of his intense research activity, he has published numerous articles in highly recognized statistical journals. So you can begin. Professor Xu, thank you for being here. The word is yours.
Yeah, thank you, Anna, for the nice introduction. And first, I want to congratulate the authors on this insightful paper. And Dr. Zhu and I wrote this comment paper. We have the following 3 comments that may improve the formulation of the proposed DIVAS method. Okay. So first, we have the comment 1. So we found the DIVAS is not defined at the population level. Okay, so the DIVAS is built at the sample level with orthogonality in the Euclidean dot product space, but not defined from the population level with orthogonality in the L2 space of random variables. Okay, so if we assume all the involved variables are mean 0, so we can see the orthogonality in the L2 space actually is equivalent to the 0 covariance or 0 correlation. Okay. So here we just assume the n columns of each matrix in the DIVAS decomposition are n ID copies of mean 0 random vector. For example, the A matrix, signal matrix. So we assume the n columns are ID copies of mean 0 random vector AK, similar for VI and the little VI. Okay. So from the condition 1 in the paper, the divisibility condition in the paper, it assumes the column space of the score matrices VI, Vj satisfy this orthogonality constraint in the Euclidean dot product space. Okay, so that actually is equivalent to assume the sample covariance matrix of the Vi and the Vj is 0. Okay, so we can see actually more precisely, it actually aims to assume the population covariance matrix of Vi and Vj is 0. Okay, so we can see actually, as we know, if these 2 random vectors are jointly continuous, the population covariance matrix is 0 actually means the sample covariance matrix is not 0 with probability 1. Okay. In terms of this, so we think maybe it's more precise to define the DIVAS decomposition at the population level. And another benefit is that we can study the statistical properties of the decomposition, such as estimation consistency. Okay. And we have another comment that the DIVAS doesn't assume the orthogonality between individual structures. Okay, so you can see the DIVAS doesn't assume the column space of the individual structures Vk and Vk prime. So if we translate it into the L2 space of random variables, it actually means it doesn't require the 0 correlation between these individual structures. Okay, so why this orthogonality constraint is important? Because we think it is necessary to ensure a complete separation between the joint and the individual structures. So let's take, for example, just take the first entries of V1 and V2. For example, if they have non-zero correlation, we can always project the V11 onto the V21, right? V21. So we can see the V21 actually can be viewed as a joint structure component of this V11 and the V21. Okay, so we think this orthogonality between individual structures is necessary to ensure a complete separation between joint and the individual structures. Okay, so our final comment is that DIVAS may be a little bit conservative from the joint structure. Okay, so let's consider a simple case, simple 2-view case with variable dimension D1 and D2 are all equal to 1. That means each view only has a single variable. Okay, say here we have for the signal variables A1 and A2. Assume they are standardized variables. Okay, And also we assume their correlation is not zero or positive or negative 1. In this case, from the condition 1 in the paper, we can obtain the AK. Actually, it's just the individual structure component VK. Okay, so in other words, in this simple case, the DIVAS is unable to find joint structure. But competing methods like DCC and DCLF, actually we recently proposed, are able to find the joint structure. Okay. So this is our papers cited in this comment. Okay. So actually these 3 comments, I think the first comment is easy to adjust because even you define from the sample level, actually it's just from the estimation perspective. So it actually can be straightforward to extend to define it from the population level, right? For the second comment, actually it's kind of difficult because, as you know, if we assume the orthogonality between the individual structures and also assume the orthogonality between joint and individual structures, then it may not be easy to define such a decomposition because of undividability problem. Okay, and the final comment, I think it may be easy to adjust it if we can relax this second comment if we assume the orthogonality between the individual structures. Okay. So finally, I want to congratulate the authors on this insightful paper, especially for the partial shared structure studied in this paper. It's very insightful. Thank you.
You're muted, Anna.
Sorry. Thank you, Professor Xu, for this, also for this really expert comments on the paper. Welcome, Professor Hannig, other co-author of the paper. So I invite you now to the speaker, Prothero, or the other co-authors, for giving a response to Professor Xu.
Yeah, thanks so much for the comments. I appreciate that there's lots of people out there that are thinking really deeply about these questions and making sure that we have the foundation to do what we want to do. I know we thought a lot about when we read your written comments about sort of the definition of the population level and what that might look like. And I know Jan had this idea that was, because DIVAS is thinking about kind of both spaces, right? Both trait and object of, is there some way to think about like the traits as almost like samples from some trait population that then sort of defines, we got like a signal component here and a signal component here that are coming from some sort of random distribution. And then that gives a rise to the random matrices that we deal with. And so yeah, lots of different ideas to toss around there. I'm excited to think a little bit more about specifically the last comment. And kind of work up some toy examples and see exactly the problem you're describing and see if it's an easy fix or not.
Okay, some other comments?
Yeah, thanks for these interesting comments. Let me say about the first thing about population versus sample. One could indeed put a Gaussian assumption on there and do likelihood and all of that kind of stuff. We made the choice of taking a non-parametric approach, and so different people make different choices. Now, about the orthogonality, I will say that is a strong assumption in our opinion. And in fact, the example Jack showed on his slide 9 was a situation where if you restrict to orthogonal, you're not going to find the interesting modes of variation that are there. But again, this gets down to personal choice. There's a principle I call every dog has his day. which is almost every method is going to be best in some situation and not in others. And so, of course, when we get into these competing examples, I've got my example, you've got your example, and ultimately it's going to boil down to some user choice here. But I will say I prefer the flexibility that we offer with the weaker assumptions. And for me, I find that orthogonality is going to rule out what I think are some interesting cases.
Okay, thank you, Professor Marron. Professor Hannig, some comment?
Thank you very much for your comment.
Sorry, we are not hearing you.
Oh no.
It's very quiet. I can hear you, but it's very quiet.
I don't know how can I change this?
No, I'm not able to hear you.
Hear me now?
Now, okay.
Yeah, the machine had so many
Thank you.
different choices. So thank you very much for this interesting talk. Your comments really made us think deeply about the question of what is the appropriate model for population, because it's as Chuck mentioned, to me it's not actually clear what it should be. Because if I send the number of people to infinity, typically that means that the number of traits, the number of genes or something might be growing as well, because we got better technology. And so somehow needs to be able to send two things to infinity, which then creates interesting questions, how that should be done. About the non-orthogonality, actually, we have this, Jack Counting has showed it, but we have this graphics that shows you when we find certain directions, what's the angle to the other direction. And sometimes I find it very useful to look at it, because it can tell me that I found a two-way joint between two blocks, but it's actually correlated with a third direction. And I think that is an interesting thing. Yeah, I would say one of our biggest weaknesses and strength at the same time is that we actually use things in terms of angles, and that leads to potentially sometimes loss of some power, because we first need to get a lowering approximation. And I feel like if things survive the lowering approximation, then they usually are properly attributed. But it's the first step where we might be losing power.
Thank you. Professor Hannig? Professor Xu, do you want to tell something more? Or?
Yeah, for the first comment, just defined from the population level. So actually, we don't require any Gaussian or other non-Gaussian, sub-Gaussian assumptions. We just can define it from the L2 space of random variables. Okay, so I think it's easy to extend. So just view the columns of the matrix, each matrix as an ID observations or copies of random vectors. So the first comment is easy to adjust. And for the second orthogonality constraint between individual structures. So yeah, I know many competing methods ignore this orthogonality constraints, because it's not easy to incorporate to guarantee the identifiability issue. So yeah, I know this is a very difficult problem to address. And even in our recent paper, the DCDLF method, we incorporate both the orthogonality between individual structures from different data views, and also the orthogonality between joint and individual structures, but we cannot guarantee the unique decomposition. Yeah, that is a very difficult question to address. And yeah, and for the final comment, I think yeah, maybe we can change the current DIVAS formulation a little bit. I think it's not hard to improve the method, especially when you have two standardized signal variables, even they have non-zero correlation. We can still find the joint structure. But currently, since even you have a highly correlated signal variables, there is no joint structure. So I think it may be not ideal. But I think I think it's not hard to improve on this aspect.
Okay, some other comments, or can we go on with the last discussion? Okay, the last discussion is Dr. Myrvoll-Nilsen, Eirik Myrvoll-Nilsen. He's a researcher in statistics, machine learning, and climate science, with a strong background in Bayesian analysis and data integration. He holds a PhD in mathematics and statistics in 2020 from the Arctic University of Norway, where he specialized in efficient Bayesian modeling for climate applications. Currently, he is a visiting scholar at the University of North Carolina at Chapel Hill, focusing on multi-omics data integration for breast cancer research. With extensive experience in deep learning, Bayesian statistics, and climate modeling, Dr. Myrvoll-Nilsen has worked as a postdoctoral researcher at UIT and the Potsdam Institute for Climate Impact Research. His research spans diverse topics, including object detection using artificial intelligence, uncertainty quantification in climate data, and early warning signal detection. Beyond research, he is actively involved in academic leadership related to the Norwegian Statistical Association and mentoring PhD and master students. He's also the creator of several R packages designed for Bayesian climate modeling and statistical analysis. So thank you, Eirik, for being here and participating in this webinar. You have the word.
Thank you very much for the very kind introduction. So since we published this comment, we have had some more recent developments that are a bit more interesting. And given the time constraint, I think I'll focus more on that in this talk. So first of all, I'd just like to congratulate the authors on this excellent paper. It brings new headway into new exciting areas and pushes the boundaries of data integration, and by incorporating matrix perturbation theory and optimization to estimate both shared and partially shared structures between different data blocks. It improves upon existing methods such as DIVAS to allow for partially shared structure that are shared between some but not necessarily all different data blocks. Identifying similar structures in diverse data is becoming increasingly important since we have more and more data available and more data sets that are increasingly diverse. And we see that also in like the deep learning field with increasing, with the emergent field of multimodal deep learning, for example. And data integration will only be more and more important as, in the years to come. So the way this DIVAS finds this shared structure, it expresses them based on these common modes of variation that are shared between the different blocks. Similar to PCA, it's expressed by outer product of these loadings and scores vectors. So if we take the example that Jack showed in his presentation, here we have, this is like the 20th century mortality data. In this case, we have 4 different blocks, and each have a set number of traits and number of data objects. If we run DIVAS on this data set, we get this very nice plot, which very clearly shows which modes of variation are shared between the different blocks. As Jack also mentioned, that if the number of traits and the number of data objects are the same for all data blocks, we can flip this around and consider here. In this case, we have years as the data object, but we could also consider age as a data object, and the data will look a little bit different in that case, but it will still have the same. The low rank approximation of output from DIVAS will still have the same rank, but the modes of variation will be shared differently between the different blocks. You can see if you compare these different methods, you can see quite clearly different in this DIVAS output plot. It's worth considering a bit why these just changing what you consider as a data object will produce different results in DIVAS. So essentially what is happening, it's that when you use years as data objects, the signal will look for modes of variation where the scores are the same for all the different blocks. But if we use age as data objects, it will find loadings that are the same, so intuitively. And this can give find different common modes of variation, and which can give you different results when you perform this DIVAS analysis. And this begs the question, are there modes of variation where both the scores and the loadings are the same? And this kind of leads into what we call, for now, double joint mode of variation. Here we have this loadings and scores are the same for all the different blocks, but they are allowed to have different scalings, so these lambda parameters. So in the mortality data set, if you use years as data objects or age as data objects, you will still find the principal mode of variation for the four-way joint space is still largely driven by reduced mortality, particularly among the younger part of the population. So they are essentially finding the same mode of variation, and it will make more sense to kind of consider that like a double joint mode of variation. If we use the same numerical optimization, we are able to identify the loadings and scores, which produces the same modes of variation as when we use years or age as data objects. It's also possible to have joint modes of variation that are of these different types in the same data set. So in this toy example, we have these observations that are made of 3 components. We have this double joint where both the scores and loadings are the same for both blocks. And we also have this loading joint where the loadings are the same for each block, and we have one where the scores are the same for each block. Of course, if we consider different types of joint spaces, then the number of possible combinations and of subspaces to explore will increase quite drastically, especially if we move beyond 2 blocks. So that is like a particularly new challenge if we move further beyond in this direction. So I guess I'll stop here, and I would just like to congratulate again the authors on this exciting paper. Thank you.
Thank you, Eirik, for your comment. Now Jack, the other authors, can give a response to Eirik's comment.
Yeah, I'm excited to see what this double idea ends up, how this double idea ends up working, especially in sort of the cancer genomics world as well, where you have maybe you could do a meta-analysis or something like that, where you have the same people at different times or all those sorts of things. Yeah, I have to think more about the implications of this structure to sort of the underlying model signal matrix breakdown of DIVAS and how that how you allocate stuff to different boxes, and how that then adds to how do we know we allocated stuff in the right boxes and all that stuff. It's an interesting wrinkle. Lots to think about.
Okay, Professor Marron or Professor Hannig?
I think an interesting thing to realize about what Eirik's talking about is up until now, we can mostly compute things with a singular value decomposition. type of analysis that underlie AGI, for example. And we don't know how to do anything like a singular value to get this doubly joint mode of variation. As far as we can see, it just has to be done with iterative optimization. And another aspect we haven't looked at all is how do we decide which modes are really there? So there's a big statistical inference question to be tackled as well. So all of these are just things we're thinking about right now.
I wonder if there's anything to be done with like the Grossman manifold or something. I know sometimes when I show this to the math colleagues, the more applied math focused colleagues at my workplace, that's the place their minds go whenever we start talking about matrices and subspaces and bidirectional and all that. So maybe, I don't know if there's anything to be done in that space for signal extraction or finding joint stuff.
Sounds like a direction you should pursue. I'd be interested to hear what they have to say.
Okay, Professor Hannig.
Yeah, I don't have much to add. Maybe there is a connection between what Eirik and what I were saying. That maybe there could be some sort of a joint bidirectional model on the population space that then itself shows itself on the observed data. It's a lot to think about.
Yeah, we are sort of facing an explosion once we start allowing some of these to be pairwise, doubly joint, and some not to. And I think we may be back to High's orthogonal decomposition as a way to sort this out. And maybe we need to do that.
Okay, Eirik, do you want to say something? Or?
Yeah, you're touching on the same problems. Like we have this, it's like very recent developments. We haven't looked into like this statistical inference stuff, which is also very important to determine whether or not the spaces are actually there, and like how to decide whether or not a joint subspace is like a double joint or if it's loading or scores. So it's a lot of different difficulties, challenges to overcome here.
Okay, thank you. Do someone in the room want to tell something more about the paper? Okay, in this case, I think we can finish by thanking again to the authors for this really hard paper from a theoretical and methodological point of view. I think this is a very impressive and nice contribution. Thank you in the name of our journal test, and especially to Professor Steve Marron, who is I think a very good friend of our Spanish Society of Statistics, and he is always willing to collaborate with us. Thank you, Professor Marron. And thank you also to the discussant for also these impressive comments of this paper. And thank you, the audience in our YouTube channel, SEIO YouTube channel, for participating in this seminar. So, goodbye. Have a nice day in the USA and a good afternoon in Spain. Bye.
Bye.
Thank you.
Thank you.
Thank you.